YouTubers and students. Dave again out in Western Pennsylvania, USA. Virtual Organic Lab. This will be video number, let's call it video number 8. Here with Beyond Labs Virtual Organic Lab, we're going to conduct an aldol reaction. Probably the most heavily cited organic chemistry reaction known, the aldol reaction. Of course, in glycolysis, anaerobic oxidation, there's an enzyme aldolase, which actually is carrying out a retroaldol. Okay, let's see what kind of an aldol we can do. These are our choices. And I'm going to select this ester. It has an alpha carbon with an H that's acidic enough. Well, I'll show you how we're going to do it. I'll double click on that. Note it's a solid in the flask. I'm going to drop in benzaldehyde, which can only accept an enolate or ester enolate. And I'm going to use nonpolar solvent. They have a choice of ethanol, water, or diethyl ether. So I'll check the whiteboard, and all three are there. I'm putting the cursor over the round bottom, seeing the two reactants and the solvent. I'll bring it down now to the stir plate. And I'm going to use LDA, lithium diisopropylamide, a very powerful non-nucleophilic base. And I'm going to use an ice bath. I'll double click on that. And then I'm going to add the LDA. It's there, nitrogen gas, and then start the reaction by clicking on the stir green button. Note the time, 10:22. Now I did this a few times, so watch what I'm going to do. I'm going to go ahead 2 hours. 1, 2. When I do that, if I check the pot, I only have diethyl ether, diisopropylamine, and the lithium salt of the aldol, the aldehydic ester mixed aldol reaction. I'm going to click on the SEP funnel. And I'm going to add aqueous acid to remove the diisopropylamine and convert the lithium salt to the molecular product. Bottom layer has lithium chloride, diisopropyl ammonium chloride, and water. Top layer has only diethyl ether solvent and the product. Now, we'll worry about the structure of the product in a minute. Now, watch what I'm going to do. It's a solid because I've done some literature searching. I've pointed out in prior videos, you can look up on the internet, SDBS. That's a database put out by the Japanese Analytical Chemical Society. Or you could look up the product and find out that it is a solid. So what I'm going to do is take it and put it in the crystallizing dish, or the equivalent of a rotary evaporator, or a crystallizing dish in the fume hood, and you see the solid residue, which is the product. Let's check the melting point of it. So what I do is I go over there, and that melting point is 130.0 degrees, the exact melting point of this compound. Let's run an FTIR. Of course, you can look up the compounds infrared in the database, SDBS. Here's the proton NMR. Let's see what else. C13. There's your proton decoupled C13 spectrum. Here's your mass spec. Be nice if I brought it over to the crystallizing dish. Okay, there's your mass spec. The molecular ion is also the base peak. And the next thing would be the structure, huh? There it is. I'm bringing the mouse button up to the blackboard, and you can see the beta hydroxy ester aldol, mixed aldol reaction between benzaldehyde and the ester. LDA, non-nucleophilic base, quantitatively pulls a proton off of that ester, quantitatively, and then it attacks the aldehyde because the carbon of the aldehyde is much more electrophilic than a self condensation of the ester component. Hey, thanks for watching. Bye for now.